The broadcast is now starting. All attendees are in listen-only mode.
Hello, good afternoon, everyone. My name is Anna Zylik, and I am with ICF. We are the vendor working on behalf of the sponsors of Energize Connecticut to bring these passive house and all-electric homes trainings to all of you. So thanks for joining us today. These trainings are at no cost, thanks to the sponsors of Energize Connecticut, and are part of a partnership with Connecticut Passive House and Build Green Connecticut. These trainings will be recorded and will be available online afterwards. A quick reminder that as part of this training and workforce development initiative, we are offering a 75% cost reimbursement for individuals pursuing either PHMass or PHI professional accreditation. So this includes the cost of the trainings and the exam. And once you become certified, we'll work with you to process the 75% cost reimbursement. So if you have any questions on that, please do not hesitate to contact us. Now we can go on to the next slide. So, thank you. In addition to this no-cost educational training series and the professional accreditation reimbursements, the sponsors of Energize Connecticut also offer robust incentives for builders and developers who choose to go all electric with their residential buildings or pursue passive house certification in multifamily projects with 5 or more units. Next slide. Thank you. The passive house incentive design for Energize Connecticut is shown here and includes pre-construction incentives for feasibility studies and energy modeling, and post-construction incentives for full passive house certification. Next slide. The all-electric incentive is for both single-family and multifamily buildings. It offers 2 levels of eligibility with specific design and performance requirements associated for each, and has incentives amounts ranging from $1,500 a unit for multifamily up to $10,000 for single-family homes. So our goal is for everyone involved in the construction of residential buildings in the state of Connecticut to be aware of these incentives. So if you are interested in learning more, please visit our website or contact us directly at the email addresses that we have on the slides. So that's it for my quick introduction. As for questions during today's session, please feel free to use the chat function throughout, and I will relay the questions over to Aaron, today's speaker. So yeah, with that, I will turn it over to today's presenter, Aaron Gunderson.
All right. Hello, everybody. Thank you so much, Anna, for the introduction and for setting up the Lunch and Learn today. So I'm Aaron Gunderson. I'm the Executive Director of Passive House Massachusetts. I've spoken to Connecticut audiences before, and I'm thrilled to be back to talk with all of you. This is Passive House 101. It's meant as an introductory level session to kind of go over what Passive House is and what it does. We do have a 201 scheduled. I believe that's next week. Is that right, Anna?
Yes.
Yeah, I believe we have. Great. Yeah, I believe we have that next week, so we can go more in depth on topics for anyone interested in joining that one in a week from now. As Anna mentioned, she'll be monitoring the chat room, so feel free to ask questions throughout the presentation. Some we might be able to get to during the presentation. The rest we'll get to at a Q&A period right at the end. But I do want to give a quick shout out to my friends at Passive House, or at Connecticut Passive House. We've done events with them in the past. A great organization there. Your local Passive House group, so ctpassivehouse.org. You can find out more about the events that they're doing there. So quick, we're going to start off with a question for you all. Which of these buildings is a passive house? Give you a moment here to take a look. See if anyone has any guesses. Feel free to use the chat room if you want to, for those who are participating today. If I could do the Jeopardy theme music, I might do that. Any answers here? Any guesses for you guys out there? Yeah, some of you are thinking this is a trick question. It is. These are all passive house buildings. And that brings us to the first lesson. What have we learned about passive house? Passive houses are not all houses. Any building can be a passive house. What's the second thing that we are going to learn right away about passive house? They're not all passive. All the buildings I just showed you have active mechanical systems for heating and ventilation. Turns out that passive house is a very misleading name, and my apologies to all of you, but it is the name that we're stuck with and the name that we're going with for this program, passive house. But keep it in mind, we're not talking about buildings that are all passive, and we're not talking about buildings that are all houses. So what are we talking about? What is a passive house? So a passive house itself as a standard is a third-party building verification program. It has two options for certification, or you can think of it as two organizations that provide certification, PHMass and PHI. I'm going to talk a little bit more about those as we go through today's presentation and explain a little bit about the differences and why there's two. But for kind of starting out, it's just good to know there's two certification bodies, and what Passive House is a third-party certification platform that can verify and certify that a building is done correctly. The standards themselves are set based on energy performance and building envelope air tightness requirements. So that's sort of where the standard for Passive House comes from, is energy performance metrics and air tightness requirements. And we'll get into a little bit of those details as well to give you an idea of what those metrics look like here a little later today. Passive House buildings are designed and constructed to meet these metrics. And they can do that with any various methods, materials, strategies, anything that the architects, contractors, engineers involved can come up with. There's no prescriptive list. There's no checklist of things that you have to do during construction. There's no points awarded in different categories. So simply these metrics that you hit at the end of the day, and however you manage to do that, you're able to do. So what do you achieve by doing Passive House? So heating loads, which are probably the kind of main focus where Passive House really zeroes in on, or at least I should say originally where Passive House focused was on reducing heating loads, and they're reduced by 90% or more compared to a typical building. This can get, vary a little bit based on what we consider to be a typical building, but it's kind of as a general statement, 90% or more compared to a typical building. Overall energy demand, so when we look at heating, cooling, hot water, plug loads, appliances, all energy in a building, that can be reduced by 60% or more. And we're going to take a look at some actual data here a little later to show how accurate this actually is. We are talking about 60% or more reduction in total energy. We also see a significant improvement in indoor air quality and occupancy comfort. We don't have enough data, I think, to really say we see a 60% improvement in indoor air quality or something along those lines, but we know there is a significant improvement. And it's becoming a larger and larger reason why a lot of developers, especially in the case of larger project developers or single-family clients who are pursuing this, are pursuing Passive House. Energy performance is one thing, but a lot are pursuing it because it just produces a better quality environment to be in. And Passive House also achieves verified performance and build quality. You have third-party assurance coming in and verifying your project, making sure it's built how it's supposed to be built, making sure the quality level is high. That way you're delivering a really well-built, well-constructed building that's going to perform to these levels of energy reduction for a long time. That's going to last for a long time. That's going to resist building failure issues that might come up in more typical projects. So these are some of the big things that, by say building the Passive House standard, you're able to achieve. As I sort of mentioned at that beginning, Passive Houses can be any building. Despite the name, we see homes, townhouses, multifamily buildings, commercial offices, schools, municipal buildings, hotels, even a hospital I'm going to show you in a moment. Any building type can be a Passive House. All three of these projects you're seeing, these are actually up in Massachusetts, but we have a school, a single-family home, and a large commercial tower. So any building can be a Passive House. This is, despite that, sorry, it says single-family home Cambridge at the bottom. This is actually a row house in Brooklyn. But this is the Passive House effect. So one of these homes was retrofitted to be a Passive House. So this is the takeaway here, is that Passive House is not just for new buildings either. you can retrofit existing buildings to be a passive house. So we're going to put on our thermal imaging glasses right now and take a look, and you can see which one of these was retrofitted to be a passive house. The green, yellow, red coloring that you're seeing, that's heat escaping the building in the thermal image. The blue one in the center, that's the building that's trapping all that heat in on a nice cool day. So on a passive house project, there's all kinds of different roles that people take on. And you as you kind of explore passive house, you're going to learn about these different roles. You're going to hear them. So I just wanted to kind of provide a little summary of them to give you an idea of what these roles are. So starting with sort of the design phase, we have what are called consultants or designers. They're usually going to be a PHMass certified consultant or a PHI certified designer. So you might hear acronyms like CPHC or CPHD. That's what those are referring to, are these certified consultants. These are the primary leads on the passive house process. So on a project, one of the first things a developer will bring on is going to be this passive house consultant. Sometimes these are in-house with an architecture firm. So whoever the architect is on the project might have the CPHC in-house. Other times they're an outside consultant who they bring in specifically for that project. It varies from project to project what approach is taken, but either way, you're going to have a certified professional involved in the project who's going to take the lead on the passive house aspects of it. You're going to have an energy modeler. This person is taking the lead on running your energy model. Passive house uses very specific energy modeling platforms. So they're either known as WUFI or PHPP. Both of them exist. Generally, those projects that are certified under the PHMass method use WUFI, and those that are certified under the PHI method use the PHPP. But both of them are similar and do similar things. They're energy modeling software. So you're going to have an energy model. You're then also going to have a certified builder or certified trade person. This is generally going to be recommended for the general contractors, maybe the project manager, site supervisor, even lead carpenters. In some cases, this is recommended. This is not a requirement. Every project is going to have a consultant and an energy modeler, but not every project is necessarily going to have a certified builder. It's not a hard requirement, but it's something that is very, very much recommended. So if you're working with a GC that is not yet experienced in passive house, it's suggested to have some members of their team, like those listed here, go through one of these trainings first before starting the project. You're then also going to have, for PHMass projects, either a rater or a verifier, and for a PHI project, something called a passive house certifier. And these are the folks that are taking sort of the lead on the final verification and certification process. They're the ones looking at all the documents, verifying the energy model that's produced, looking at all the build documentation from the construction phase, and making sure that this project meets the passive house requirements. So those are sort of the main roles that you're going to see and going to hear about throughout passive house. So now let's look at sort of why we actually do this. What are the benefits of passive house? So this slide sort of, breaks them down into three categories. We have our financial benefits, health and comfort, and environmental benefits. So in the financial benefit category, we're looking at reduced energy utility costs. If we're reducing heating loads by 90% or more, that means we're reducing your heating bill by 90% or more. It's kind of pretty easy to make that connection. So we're seeing significantly lower utility bills in these projects. I should also mention, along with significantly lower utility bills, we're tending to see much more consistent utility bills from month to month, rather than there being big variations from month to month or season to season. We're seeing pretty typical bills, which means it's much easier for owners and tenants to plan because the bill's predictable. We're also seeing reduced equipment maintenance costs. This tends to just, mainly this is a factor. We're just using a lot of newer equipment in these buildings, but a lot of it can come also from the fact that we're using smaller equipment, equipment that doesn't have as many maybe parts to it. So we're seeing some reduced equipment maintenance costs. And we're also seeing longer lasting construction. So what that means is that there's less issues that have to be addressed in the years following construction. Less callbacks for the contractor to come out and fix something, less issues that come up for the homeowner, for the tenant to have to deal with. So simply, lower costs being put into repairs. So that's sort of financial benefits. In terms of health and comfort, I hit on a little bit of this earlier, but we're seeing improved indoor air quality inside these projects. I'll get into a little bit about why that is a little later, but really we're controlling the air movement through these buildings, and the air that is being provided, where we are filtering that air. So that's kind of one of the main ways we're providing high levels of indoor air quality. We're also seeing things like reduced air drafts and other things related to comfort. Along the same category, I would put consistent temperatures. So in a building, from room to room, floor to floor, the temperature is much more consistent. You're not having that variation. And quieter acoustics. This is actually one that I started talking about after talking to a lot of tenants in some of these buildings. Actually took a tour many years ago of the distillery, which was one of the first multifamily projects in Boston, and talked to a few of the renters. This is a market rate rental building, so a few of the renters there, and everyone would bring up how quiet it was, which I found surprising, but then realized it was a pretty big benefit. This was in South Boston, a busy area. When you're inside that building, you're not hearing any of the noise outside on the street, whether it's garbage trucks going by or anything else happening out there. You're not hearing it. And also the mechanical equipment itself tends to produce less noise than your typical mechanical equipment. So you're producing less noise on the inside. So quieter, more comfortable, and better air quality. These benefits are enormously important and becoming much, much larger part of the conversation. In many cases, superseding the financial benefits and the environmental benefits as the key reason people are choosing passive house. The environmental benefits at the bottom, I put them at the bottom. They're sort of the core reason passive house was created in the first place. So I don't want to take them for granted, but they are, in some ways, not the key driver for people making the decisions anymore. I think for the first movers who did this originally, they were the biggest benefit, but for folks nowadays, it's the health and comfort and financial benefits. But the environmental benefits need to be talked about, need to be mentioned, because they're enormously important. We're seeing reduced carbon emissions. If we're using less fuel, yet less fossil fuels to heat and cool our buildings, we're going to be producing less carbon emissions. We're also building a much more climate resilient building. I'm going to talk a little bit more about that in a moment and what I mean. And we're also providing a platform for other sort of large scale environmental or carbon reduction goals like electrification and net zero. A passive house, just to clarify, the passive house standard does not require the building to be all electric. Currently, buildings can still have gas lines in for, say, heating or hot water and meet passive house. You can also have a building that does not have solar and it's not net zero and meet the passive house requirements. So those are not required, but passive house provides a really good platform for the building to achieve those goals. So this is a little bit on that climate resilient piece I'm going to tell you about. Climate resilient sort of means a lot of different things. This is just sort of one aspect of what climate resilient means, but it's, I think, a pretty critical one. So this home you're seeing was an existing building that was retrofitted in 2020 to be a passive house, finished in 2020. And then a year later, in 2021, Texas had an enormous deep freeze in winter. Their power went out at the same time. This has been happening more often in Texas. The grid's been having a lot of challenges, but this story is from 2021. So this homeowner in this newly renovated passive house, the power went out about 1 a.m. When they woke up that morning, it was 9 degrees outside, 62 degrees inside their house. Their neighbor's house, which was not a passive house, was already down to 36 degrees. That's 36 degrees is not comfortable, and for many people is quite dangerous. So that a passive house allows us to, even though we are relying on mechanical equipment to produce our heating and cooling and ventilation, when that mechanical equipment isn't working because of a power outage, we're able to keep that heat in for a longer period of time before it dissipates to the outside. So that is one way that we talk about a climate resilient building. No matter what type of extreme weather conditions are happening on the outside of the building, what type of power outage situations are happening, you can maintain a comfortable temperature or comfortable living conditions for a lot longer, and hopefully withstand the duration of those extreme weather conditions or those power outages. As I mentioned, Passive House provides a really excellent pathway to net zero. This is just kind of one example showing you that this building is the Bullitt Center in Seattle. They designed this to be net zero from the very, very beginning. Their first sort of a model of solar predicted that they needed an entire city block's worth of space for solar panels to produce enough energy to be net zero. So they went back to the drawing board, redesigned the building, and designed it to meet Passive House. Which basically meant they lowered their energy demand even more significantly than they originally intended to. And then they could fit all the solar on the roof that they needed with a little overhang. But that's kind of the main idea of what we mean when we say Passive House provides a platform to net zero. By focusing on that high level of energy reduction, we make it possible for buildings in a lot of cases to fit enough solar right there on site to be net zero. And also want to kind of add that affordable housing and Passive House are a great mix. Here in Massachusetts, we've seen enormous support for Passive House from the affordable housing community. Just last year in 2023, we saw about 40% of affordable housing projects in the state were attempting to achieve the Passive House standard, which is pretty incredible numbers. I don't know what they are in Connecticut, so I can't share those with you, but I do know that Connecticut is one of the states that awards extra points in their qualified allocation proposal plan, the QAP, for Passive House projects. So if you are going for affordable housing financing in the state and you are pursuing Passive House in your proposal, you're given extra consideration. So Connecticut has done that a while ago. The number of points have kind of varied every time they release a new draft of the plan, but it's there, and it's an enormous benefit and incentive for affordable housing projects to achieve Passive House. A little bit in terms of cost. These numbers are from Massachusetts, so that's kind of the data that I have at this moment. But the Mass CC here funded several different projects with the goal of proving or showcasing how Passive House could have low costs. Their goal, I think, was a 3 to 4% cost premium. They wanted all their projects to have less than that. They ended up with an average of 2% cost premium on all these projects. And it's worth noting that this was done in 2018. So these projects are at this point old. We expect most new multifamily projects to be in that 0 to 1% sort of cost premium category. The costs have come down dramatically. I will say there's, for those out there involved in, say, single family projects or commercial office projects, those numbers vary much more widely. Some of them can be close to cost premium. Some of them can be dramatically more expensive. There's a lot more variation. When it comes to these multifamily projects, this is where we're kind of seeing that cost premium really just kind of settle in at a pretty low number. Here's some more data just to sort of showcase this. This is from Pennsylvania. I mentioned that affordable housing financing that Connecticut is doing. Pennsylvania was actually the first state to do that. They started in 2016. The first year, which would have been at 2016, they had so of all the projects that were awarded affordable housing financing, they awarded about, some of them were Passive House, some were not. The Passive House ones had about 2% more costs associated to them than the non-Passive House ones. And by 2018, the Passive House projects were about 2% less, which was really surprising to see. But on average, they're seeing, pretty much cost parity. So really, between projects achieving Passive House and projects not achieving Passive House, cost is not a factor. That's basically what their data is showing them. So that was cost data. Now we're going to look at performance data. So energy performance. So as I mentioned at the beginning, kind of one of the goals of Passive House is around a 60% or greater reduction in total energy demand of the building. So these are some projects. This is the distillery. This is actually the first multifamily project that was built in Massachusetts. And this is data from that project. So we're looking in this case at EUI, or energy use intensity. But this is basically taking the total energy use of the building and dividing that by the square footage of the building to sort of normalize it. So in general, similar multifamily buildings in the Boston area average around a 62 EUI. The distillery achieved a 24, or 60% less energy. So exactly what we hoped it would. This is Guilford Village. This is a project up in New Hampshire. I wanted to showcase this one because they built this in multiple phases. There were 3 phases. The first one you don't need to worry about, but the second one they built to LEED standard. And then the third one, they built the passive house standards. Other than achieving passive house, the third phase was fairly similar to the second phase in terms of architectural style and sort of all of those type of features. So it's really just the extra things they needed to do to achieve passive house that made it different. And you can look at the UI. They went from a 62 in the phase 2 lead building to a 24.7 in the passive house building. Incredible improvement. Lastly, this is one more slide on energy performance just to show you some different data. This is from Pennsylvania again. As I mentioned, they were kind of the first state to take a big jump into the affordable housing passive house world. So now we're looking at some of the projects that went through that affordable housing financing. These were all various dots on that chart I showed you earlier. But in this case, we're comparing the blue bars are just regular kind of code-built projects. The ones that are orange were ones that were built to achieve LEED, and the gray ones on the far left are ones that were built to achieve passive house. And you're seeing the UI compared. So the first obvious takeaway is the average UI is dramatically lower for the passive house projects than it is for either LEED or general code-built projects. But the other kind of takeaway that I like about this is it shows you the variability. Code projects are kind of all over the map. Code doesn't require you to have a low EUI, but as you can see, some projects achieve it because you can, and some projects go ahead and have, for whatever reason, end up with a lower EUI. Average code projects do not. They have a really high one, but it's all over the map. LEED projects, on average, have a lower EUI than code-built projects, but again, high variation. Some of them are not going to be very well performing in EUI. They may have focused on other aspects of the LEED programs. They made more attention to other sustainability features that LEED awards. So maybe energy wasn't the focus and you have that variation. When you get down to passive house, not only are you having that lower average energy use, you're also having greater predictability. And that's one of, again, the features that I mentioned already, and I'm going to kind of mention a few more times, that passive house delivers much higher level of predictability. You know what you're going to get when you go into building a passive house. So those are the questions. So that's a little bit of background about what you achieve with passive house, why it's important, all the benefits that we get from it, some of the energy performance and cost data. What I'm going to move on to now is talking a little bit about the passive house standard itself. So getting to a little bit about what it is, where it comes from, what are the metrics, that sort of thing. We're doing pretty good on time. I haven't seen any questions come up. If you guys have them, remember, jump in, ask questions, let me know. I can address some while I continue to talk, and the rest I can address at the end of the presentation. And as I mentioned earlier, there are two organizations that certify passive house projects. So there's the Passive House Institute, or PHI, and then there's the Passive House Institute US, which is generally just known as PHMass. Both of these organizations exist at the same time. They both create and manage their own passive house standard, and they both certified buildings right here in the US. So despite PHMass being the US version, they both certify buildings here in the US. And in Connecticut, there are projects certified under PHMass, and there are projects that are certified under PHI. And to be clear, you would not achieve both of these. Any project, you're going to pick one of these to go with. They're very similar, but they do have their slight differences. But either way, they're both going to manage the passive house standard. They're going to define the metrics and criteria for what you need, and they're going to provide that certification for buildings. And they're also going to both provide that accreditation for professionals that I mentioned earlier. The certified passive house consultants and designers and so on, those are being accredited by these organizations. Passive House Massachusetts, Connecticut Passive House, we're not certifying projects. We're not accrediting individuals. It's these two organizations that are doing that. For the record, this building I'm showing you in the photo on the right is in Germany, and this is actually the first passive house building that was built in the early 90s. It was actually the prototype passive house that PHI, the Passive House Institute, used as their first sort of model for what a passive house can look like. And I like showing it. This obviously image cuts it off, but this is a multifamily building. So from the very beginning, passive house actually started with multifamily buildings. I think a lot of the times, mainly because of the name, we always picture a single family house as a passive house. But in many cases, multifamily buildings are far more common for passive house. So here's kind of a quick timeline. The concept of passive house actually originated here in New England. That home I'm showing you is up in Massachusetts, that super insulated home on the left. But around the 70s, people became very, very concerned with high energy costs and finding ways to reduce energy demand in homes. So we saw a lot of really just super insulated homes, thick walls, just super insulated. That was also the time where solar, like water heating, became pretty common. You saw solar water, solar thermal panels being put on homes, things along those lines. That was kind of the concept, the genesis of Passive House. But as an actual standard, Passive House was created in the 90s. Again, you can see the building in the center. That was the prototype. And right there in the mid-90s, the Passive House Institute formalized the first Passive House standard that buildings could achieve, and buildings started to achieve it. In the mid-2000s, PHMass started their own organization here in the US as a spin-off of PHI. They eventually became their own organization with their own standard. So that's a very brief look at the history of Passive House, but that's how we got to where we are today. Again, I think just the important thing to know is that there's two standards out there that provides some sort of market choice. You can look between the two of them and decide which one you want to pursue for your project. So what are these requirements? I keep talking about energy performance metrics and requirements. What are they? So Passive House requires performance criteria and then some other things. We're going to talk about performance criteria today. That criteria is divided in kind of three buckets. You have your heating and cooling demand. So that's how much energy you use to heat or cool your building. You have whole building air tightness. So simply put, how airtight is your building, how much air is moving through it. And then your source energy demand. Source energy demand is just a way of thinking about overall energy use of the building. For those out there familiar with the difference between site energy and source energy, we're pretty consistently talking about source energy. But for those unfamiliar, we're not going to get into it right now. If you have questions, ask. But PS and PHI are both concerned with overall source energy. And it's good to know there's other criteria. We're not going to talk too much about them today. But the Passive House standard, when we verify buildings and make sure they're being built correctly, we are looking at things like ventilation rates and moisture management and other kind of things that go into the building beyond just performance. But those are the big ones. So this is just showing you, it's just kind of a visualization of kind of what these metrics are attempting to do. So on the right, what you're seeing is sort of an old leaky house, and you're dividing this on the top and bottom between heat gains and heat losses. So let's think about heat gains and heat losses. You can think about this in terms of cooling gains and cooling losses as well if you like, but that's a little bit different. So we're just going to focus on heat gains and heat losses for this, but just to give you an idea of what we're talking about. So in general, in a leaky building, you have all different sources of heat losses there at the bottom. Heat is being lost right through your walls, through poor insulation or lack of insulation. It's going up through your roof, you're losing heat through the floor, or you're either bringing any cold air in through the floor. Your windows are leaky, your doors, you have inadequate ventilation systems. You then have your heat gains. Your heat gains are meant to make up for those heat losses. You have some heat gains coming from solar heat gain. So in the winter, you might have some sunlight coming through your windows, helping to produce a little bit of energy, of heat energy. You also have internal heat gains. That's us, we're people, we produce heat. Your appliances produce heat. There's other sources of internal heat gains. You can see though, they're pretty small, solar and internal, you can see are small on the graph. So the vast majority of the way that we replace all those heat losses are through our heating systems. When you get into a more modern house, what you're trying to do is reduce the amount of losses so that you can have a smaller heating system. Pretty simple. Passive House does that at a very dramatic level. We're putting a lot of focus into reducing those heat losses through the walls, through the roof, through the floor, through the windows, through the ventilation system, so that we don't have to produce much energy at all. We still have to produce a little bit, but not much. In fact, when you look at it, what you can see is that the amount of heat gains we're producing from the heating system is about the same amount of heat gains we're trying to get from the sun. If you can imagine how little heat that is, that's what we're trying to produce in these buildings. That's how little is required. That's kind of a way to think about it. We're minimizing the heat losses in order to minimize the heat gains. So what are the actual metrics? This is going to be the one time I really talk about numbers. If you like this slide and you want to get more in detail with this, join us next week. But we're going to talk about heating demand right now. 4.8 kBtus per square foot, up to about 6.5 kBtus per foot. So what does that mean? What this means is if you're building a Passive House project, you're going to have a heating demand metric that you're going to have to achieve. that metric is going to vary from project to project, but it's going to be about in this range of 4.8 to 6.5. So let's say it's 4.8. That's going to mean the max amount of energy that your building can use per year. This is per year for heating. It's 4.8 kBTUs per square foot of that building. So to put that in perspective, an old inefficient building might be, let's say, running on natural gas, might be in maybe 55 kBTUs per square foot. So we're seeing pretty dramatic reduction right there. You're also going to have goals for cooling demand, a separate number for cooling demand. That cooling demand is also going to vary from around 2.5 to 4.8. Now, these numbers, I should clarify, are for us here in the New England area. Generally speaking, metrics can vary a little bit depending on where you're located. And in more cooling dominant climates, you might be allocated a little bit more for cooling and a little bit less for heat. But here in the New England area, we generally see the metrics for heating being about 4.8 to 6.5, and the metrics for cooling being about 2.5 up to 4.8. But again, that's the maximum you're allocated, and you have to achieve that. That's fast. You then also have source energy demand. So this is that overall energy use of the building. So about 25 kPUs to around 35 kPUs per square foot. This, you could also think of this number. We're calling it source energy demand, but this is also equal to source EUI. So for those who are familiar with EUI, this is that same number. And just for reference, the average multifamily building in the U.S., new multifamily building, has 118 EUI for source energy, 118. So that's the difference. We're going from that average of 118 down to a maximum of 25 to 35. Pretty dramatic reduction. Again, these are general numbers. When you're actually going for certification, you're going to work with PHS or PHI, or for those of you who you might also be working with your consultants, but you're going to be working to get your specific numbers provided. These are meant to be general ones to provide you some guidance. And again, just to show you, here's that graph showing you that multifamily building energy use comparison. The number I cited at 118 is from Energy Star data. Pretty dramatic reduction, I'd say. So those are the energy performance metrics. I also talked about air tightness. So this is what we're looking at. The general building energy code requires around 3 air changes per hour at 50 pascals of pressure. If that doesn't mean anything to you, don't worry about it. But for those of you who kind of know what we're talking about when we say ACH, you'll probably see this and get a clear idea of the difference. A passive house requires 0.6 at the maximum. So your building needs to achieve 0.6 ACH, 50 or lower. The photo is showing you a blower door because this is measured on site with a blower door test. They actually run a whole building blower door test as sort of the final step in construction. When everything's finished, you're going to run a whole building blower door test, and your goal is to achieve that 0.6 or less. And I like showing this on kind of a separate slide with sort of big numbers like this, because I find for most project teams, this is the key metric to look at. These numbers right here, you're going to know these from the very beginning. You're going to work these into your energy model. You're going to modify your design to meet these and make sure your energy model shows you meeting these. So why I don't want to say this is necessarily going to be really simple to me, I just want to say that you're going to figure out early if you can do this or not. This number here, you're going to figure out if you can do it, but actually doing it takes focus throughout the entire phase of the project, particularly during the construction phase. There's so much that happens as the building is constructed that influences this metric, from everything from that air barrier being put up to every time some sub is coming out and putting a penetration through that air barrier. How is that being sealed? How is that being taped? There's so many things that can influence this metric that it takes a lot of focus. So for most teams out there, this is the real number that the whole team is sort of focused on hitting. A little bit about the process is sort of how to think through the steps in a passive house. So you're going to start with the sort of pre-design phase. You're going to suggest that you could start by conducting a passive house feasibility study. As Anna mentioned, this is funded through the incentive program. You can get a feasibility study funded up to a certain amount. that was listed on that slide. So a really good opportunity to just dive right in and see if this works on your project. Do the feasibility study. During that process, you're going to work to sort of choose a pass-fail standard, as I mentioned, PHI or PHS. So you're going to kind of pick which one you're using. You're going to register or pre-register with that organization. So either PHS or through a PHI certifier. And then you're going to bring on your pass-fail consultant or designer. And you might not do that in that order. You might actually do a pass-fail consultant first, and then that pass-fail consultant will be the one that helps you figure out, say, which certification standard you're going to achieve, for example. But those are going to be kind of your early pre-design steps. And then you're going to get into the design phase. So now you're going to work with your consultant. The whole design team is going to work together with them. And when I say the design team in this case, I mean, of course, the architect, but I also mean your structural engineer, your mechanical engineers. They should be involved early, helping you make sure you're designing the right mechanical system for the project, for example. But you're going to be working with the consultant. You're going to be working with the energy modeler, who's going to run an energy model. And this is going to be kind of the integrative sort of approach. You don't just design and then model and then build. You're going to design, model, and you're going to modify the design, modify the model, probably modify the design again. You're going to do this kind of a few times until you sort of have the design you want that meets your model and meets all the other requirements of your project. You're also going to be working during this phase. You're going to be submitting your model and your design to PHS or to your PHI certifier. They're going to provide you with feedback as well. So there is assistance with this. You're not left to your own devices. You're going to have feedback. You're going to have folks there to answer your questions. So after all that, you have the building designed. The model is showing you the numbers that you want to see. You move into the construction phase. So here you're going to have your contractors and trades. They're paying extra attention to those pass-fail details. As I mentioned, they're really focused on the air barrier. That's what this slide is showing you. This person is currently putting tape over a SIGA air barrier membrane. Very critical phase. I can't emphasize how important taping actually is on these projects. Using the right tape product and applying it with the right amount of pressure becomes really critical to making sure that air barrier is applied correctly and is working the way it's meant to. You're also going to have on-site verification during this phase. So during the construction phase, there's going to be maybe, say, your PHS verifier, for example, is going to be on-site at different points, inspecting the project, taking photos, checking over the air barrier, looking, for signs of leaks or things that might need to be addressed. You're also going to run blower-door tests. There is, as I mentioned, that final step is the whole building blower-door test to make sure that you hit the metric. But honestly, projects are running multiple blower-door tests during different phases of construction as sort of pre-checks or just to sort of help them make sure they're on the path to meeting it. And then you get to your last phase, certification. Yay! You're going to get your plaque, you're going to get all the information, you're going to be certified. You have built a passive house. Way to go. So there you go. It's not that different from a normal project. In a lot of cases, it's simply bringing people together early, making sure you have that whole team together and on the same page, and making sure you're paying attention to those details. Things like the air barrier, for example. So now I'm going to show some slides of just some examples. You can kind of get an idea of what projects we're talking about. I'm going to start with some right there in Connecticut, and then we'll take a look at some kind of around different places as well, just to get a different idea. But here's 11 Crown Street in Meridian. This is so this project, we're looking at the townhouses now. This project also had a separate multifamily building. So 3 buildings, 63 units, all passive house there. I'm not going to go into too much detail about all these projects. On the left, you're going to see things like developers, architects, consultants. In some cases, I'll have the contractor listed, just different information that I was able to gather from PS or from PHI that they provided. But this is just meant to kind of give you an idea of what projects look like. What we're trying to shoot. Sorry, looking at the time here. Oak Tree Village. This is another multiple building development. They have 2 buildings, a total of 17 units between them. You're seeing one of the buildings off to the left in this photo. In the center, the one with all the solar panels, that's actually just more of that's like a community center building for the development. So that one I don't believe is actually certified passive house, just the residencies were. But you're seeing the team there. Pretty cool project. This is Rocky Neck Village. This one, the picture looks a little fuzzy, sorry, but this is a pretty enormous project. 50 different units of kind of townhouses, a couple different styles, and 3 bedrooms. They also had 6 ADA compliant, I think, single family buildings as well, but pretty enormous development, all built to certified passive house. The Tyler, this one I love talking about in East Haven. This is, well, you can see the photo of it. This is an old high school that was closed down, and rather than being demolished or anything else happening to it, it was retrofitted to be a passive house senior living facility. Pretty incredible project. They did a lot of steps to go through this, a lot of work to do some modeling and figure out, how they could keep this, as much of this envelope intact as possible. But yeah, still achieve passive house. They came all, when we go next week, for those who are joining us, I have a couple more slides about this, kind of talk about some of the approaches they took. A pretty incredible project, a retrofit there. Now I'm going to jump up here to Massachusetts. This is Finch, Cambridge. That photo I showed you of that guy very carefully applying the air sealing tape, that was on this project. So this is all affordable, 98 units, affordable housing. This is Tracy Community Housing. This is a split between affordable and market rate. This is up in New Hampshire. I like this one because this project set out the developer and the architect that you can see listed here, Twin Pines and McClay. They had no experience with passive house before starting this project, and their goals were net zero. That's what they tried to achieve. You can see the solar panels in this image. That's what they wanted to get, and they were really, really struggling to do it. And through the process of figuring out how they could achieve passive house, how they could achieve net zero, they came to discover the passive house standard and ended up applying it to the project and achieving net zero. So this is one of those examples of how I mentioned passive house being a platform for net zero. Well, sometimes we see people achieve passive house and then apply net zero to that. We also see it the other way, like this, and like that Bullet Center project I showed you, where the goal might be net zero from the beginning, and the project tries to figure out how they can achieve that goal, and passive house becomes the solution for that goal. And that's what it was in this case. Also, those the black panels you're seeing on the side of the building, those are also solar panels. It's kind of cool innovation they put there. This is the south side of the project. They only put them on the south side there, but pretty cool innovation there. This is a university residence hall, another kind of building type we're seeing more and more of in the passive house world. I mean, this is still a residential building, so in many ways this is not all that different from a multifamily residential building. But obviously dorms are a little bit, there's some different things that are considered in them that are not in regular buildings. There's also more common space and study areas that are in these and some other things. But this one was for Wheaton College in Norton, all passive house. This is actually steel framed. Most of the projects that I've been showing you, the new builds, are all wood framed. This one is steel framed. For some reason, in this area, we're just seeing more and more wood framed projects, especially in these multifamily buildings. But that doesn't mean you can't do a steel frame project or any type of metal framing. There's more considerations you have to keep in mind when you do that. And I'll talk about a few of those here in a moment. But that's what they did on this project. Winthrop Center. This is that large tower in downtown Boston. This building actually features the largest certified office space in the world for passive house. So right now, they'll probably be beat before too long, but right now, this building holds the record for largest certified office space in the world, at over 8,000 square feet of certified office space. You can see 2 images here of it under construction and built. And they use actually a really cool panelized system. It's really hard to tell in this photo, but if you look at the one under construction there in the middle, all of those sort of glass panes that are the wall panes, those were all panelized. They were built off-site, very large panels that were shipped on-site and assembled sort of on the building. So pretty cool innovation in construction. And we're seeing that concept of prefabricated construction, whether for a panel or in some cases a modular style, being used more and more often with passive house as well. This is Northland Development. This is in Massachusetts as well, but this is going to be one of the, or if not the largest development in the country for passive house. They're building over 500 units, 8 buildings certified to passive house. Just an enormous development. This developer, Northland, they started, well, originally they were not going to do any passive house, but then they worked with the town of Newton, who was really pushing passive house, and they were going to do, I believe, decided to do 2 buildings to the Passive House standard. And then on their own, through their, their initial sort of the early design phase, as they were going through the feasibility studies and working with their consultant on those 2 buildings, they decided to go ahead and do 8 buildings. It just made sense to them to do it. So they went ahead and jumped in to the deep end on that one. And this is a really exciting project there. A different type of project. This is a library in Pittsburgh. Just wanted to show you the variety of Passive House. I mentioned, of course, at the beginning that any building can be Passive House. And while that's true, I'm showing you a lot of multifamily buildings because the vast majority of Passive House we see going up, especially in New England, are multifamily buildings. But it doesn't mean other buildings can't achieve it. We're seeing schools, we're seeing offices like I showed you. And here in Pittsburgh, they built a library, Passive House. A note that they put here, this was the first certified Passive House library in NA, that's North America. And this building, which they noted, used 40% of the energy of the previous library building, despite being 2 to 3 times the size. So they dramatically increased the size of the building and still used 40% of the energy of the old one. This one I showed you in that very early picture, and I was sort of asking you what buildings were Passive House. Well, as I said, all of them were, and that included this one, the car dealership in Alberta. Somehow they achieved Passive House. Pretty amazing achievement for a car dealership. Obviously, they have a large showroom. They even have a little, service area, of course, but they achieved it. This is a laboratory. We're seeing, increase in laboratories. We don't have too many examples of large laboratories. This is a small one, but it is a building type we're seeing sort of seeing increased demand in. So hopefully we're going to see more and more labs kind of meet Passive House, but it can be achieved in labs and it can be achieved in hospitals. This is Frankfurt. It's not the only hospital. There's a couple more in Europe. There are no certified hospitals in the US yet. Well, I should say there's no certified people hospitals. There's an animal clinic that is certified Passive House. But this is the first hospital. And there's been a couple more in Europe. Hopefully we see one here in the US before too long. This was dramatic. We had a presentation on this that you can see it from our website that talk more in depth on this, but the sort of things they went through to not only make this Passive House, but to figure out how they could reuse a lot of the waste heat that they produce just through the use of the building. They're actually able to capture a lot of it and use that as some of the heating sources, which really helped them construct this Passive House. So those are some examples. Now we're going to get into features of Passive House. So this is going to be sort of an introductory, level discussion of the features of Passive House buildings. All of the things I talked about here, I'm going to dive much more in depth into next week. But this is meant to kind of give you an overview. So all these buildings I just showed you, what are they doing to achieve Passive House? Well, these are the main things. So we can divide them into building envelope and mechanical systems. So in the building envelope, we're looking mainly at continuous thermal insulation. So you can think of that as throwing a sweater around the building to keep the heat in. We're also making an airtight envelope. You can think of that as putting a windbreaker over your sweater on a windy day. As we all know, that sweater might not keep the wind out, but wearing that windbreaker does. And that's what the airtight building envelope does. Then we're doing thermal bridge mitigation. So this is, identifying places where there's weak points in the envelope where, there's not insulation or some other material, or mitigating that impact. We're using better performing windows and doors. And we're optimizing these projects to take advantage of solar heat gain. So we want to increase the amount of sunlight we're getting into these projects in the winter. We also want to make sure we're not getting too much sunlight in the summer. So we want to use different types of shading features and overhangs and other things to help make sure we're not overheating projects in the summertime. So those are the building envelope features. Those are all the things that you can think about. If you think about that earlier slide comparing heat losses and heat gains, these are all the things that we do on a project to minimize heat losses, or focusing on the building envelope. We then have the mechanical systems. These are the ways that we actually provide heat or provide cooling and ventilation, but we're mainly using balanced and continuous ventilation systems. I'll talk about this in a moment. We're also using efficient and minimized heating and cooling. Again, I'll talk about this in a moment, and efficient water heating distribution. So as you can see, the word popping up a lot: efficient, minimized, balanced, kind of keywords there for mechanical systems. But we'll talk a little bit about those as well. But these are the key features of Passive House projects. So I want to focus a little bit on the building envelope. The key things, and again, I'm going to emphasize this. I have emphasized it. I'll say it again, but we're providing one, a thermal barrier around the building, and two, we're creating an airtight barrier around the building. So if you go to the top one, thermal barrier, the main kind of ways we're doing that is through some sort of dense packed frame cavity insulation. So, you know, dense packed cellulose, dense packed fiberglass, sometimes mineral wool. There's all sorts of different materials, and we'll dive more into that next week in terms of kind of what common materials are being used in this area. We're putting as much insulation into those cavities as we can. We're then putting a continuous layer of insulation around the outside. This project you're seeing in the photo, this is the distillery in South Boston. But this project, the brown material you see is mineral wool. And in this case, that is the continuous layer of insulation. That mineral wool is wrapped around the whole building. We're then also reducing thermal bridging. I'll talk a little bit about that here in a moment, but we're simply, in the case of a building like this, the thermal bridging is mainly coming from the wood studs, from the framing. Those wood studs have no insulation. They have an R value of about 1. So they're good at conducting thermal conductivity, so we want to limit that. One way we do that might be by spreading the framing members out a little bit more, rather than say 16 inches on center, we do 24 inches on center. That reduces the amount of thermal bridges. That continuous insulation layer that wraps around also reduces the impact of thermal bridges. It provides some level of insulation for those. Then we're going to create an airtight barrier. So this is a continuous air barrier around the whole building. And I do want to emphasize that it's continuous. This is very, very critical and important. And we're going to spend a lot of time next week talking about how this is achieved. But we want to make sure that, so not just the wall, when you put a wall, in this case, this photo, the green material at the very top is zip system sheathing. Zip system provides a dedicated air barrier, and the black lines you're seeing going down that green, that's the tape that's taping the seams together. So if you apply that zip system correctly, you tape the seams on the wall, you have a dedicated air barrier. But you're going to do the same thing on the roof. You're going to put some sort of air barrier down by the foundation, and you're going to find out a way to connect those together. And it's very important that all those things are there, all of them are connected to one another, and that air barrier is continuous. Tape and seal penetrations, elimination of air gaps. Again, we'll dive into a lot of these things next week. I'm going to show you some examples here in a moment, though, so we can talk about them today. This is one example of what a wall might look like. There's all sorts of ways that a passive house envelope can be designed to achieve these goals. So don't look at this and say this is how you must build your building. This is just giving you an example. A lot of times when you look at building science, or you think about learn about different assembly types, you learn about the 4 control barriers: the air barrier, the heat barrier or thermal barrier, water barrier, and vapor barrier. So this slide is just kind of showing you how those barrier systems relate to the wall that's being built. So this wall, you can see the inside is on the left. So we're going to start with drywall. We then have a 2x6 stud system that they're calling out here, dense pack with high density fiberglass. And then they put the zip system on that, Roxol mineral wool product, a rain screen, and then siding. And you can see the air barrier is being provided by that zip system sheathing, which in this case is a dedicated air barrier, again, when it's installed correctly. Then you have your heat barrier or your thermal barrier, which there's 2 levels of in this case. You have your dense packed cavity insulation, and then you have your continuous insulation around the outside. So you have 2 different places where your thermal barrier is being provided. Water management is being provided by a few different things. You obviously have your siding that's meant to sort of keep bulk water from getting in. As we all know, water can get in though. So you have sort of your rain gap or your rain screen area, which allows your wall to dry out when it does get wet. And then you have your mineral wool. Mineral wool is going to keep water from actually getting into the rest of the product. Mineral wool does a really good job not necessarily soaking up water, so it's good at keeping that out. So in this case, you have those 3 levels of your rain barrier or water barrier. And then you have vapor barrier. And I should clarify, vapor management is really the proper term, because in this case, if you'll notice, this is a vapor opening assembly. There's not a dedicated vapor barrier. And that's something that we see in a lot of projects. We also see vapor barriers used, so it varies from project to project. But the key about vapor management is providing a way for that assembly to dry out. In this case, the rain barrier is, or that rain screen is really key in helping the whole assembly be able to dry. So we'll dive into more of these details next week, but here's just some photos so you can get an idea. This is a project going up in Roxbury in Boston. You can see them kind of putting up right now. They're using, the top left photo is showing you, they're using just sort of a basic traditional sheeting. Obviously, I showed you zip system as a common sheeting element, but we also see just traditional sheeting, you know, OSB sheeting being used. If that happens, you need to provide another air barrier. So that blue material you're seeing going up is an air barrier membrane that gets put up on this project. On the bottom left, you're seeing them do the taping of it around the window bumps. So you're seeing them around the rough openings of the windows. They're doing the full taping for the air barrier so that they connect the air barrier to the inside of the windows. Then on the right, you're seeing, well, they're putting the siding up in this case, but this is showing you the insulation. In this case, mineral wool, the air barrier system that they're using, or sorry, not the air barrier system, I apologize, the rain screen that they're using, and then the siding being attached to that. This is that Finch Cambridge project. So you're not seeing the sheeting here, but they use the typical sheeting, OSB style. They put Siga over it. They use this in the top right. You're just seeing some type of like a girder system. This is called Cascadia clips, but it's just a way to help adhere both the mineral wool and the siding to the wall and help minimize the thermal bridges that are going through that envelope. I mentioned, you know, wood studs being one example of a thermal bridge. Well, fasteners are another example because they go right through the wall and they're usually metal, so they're going to, you know, transfer heat right through them. So there's different methods of, you know, when we install insulation on the outside of the building or install siding, there's different methods used to either reduce the amount of fasteners that we're using or to use different types of systems that minimize how many fasteners are going all the way through the wall rather than just going part of the way through. So there's different methods to do that, but it's something to always keep in mind about these projects as well. That air barrier can be a really well done air barrier, but if you're putting too many penetrations through it, you're going to dramatically weaken it. This is that Wheaton College project that was steel framed. These pictures are a little out of focus and hard to see, but the key concept here is that you can see it a little bit. They're using a Siga air barrier. They also use mineral wool on this project. The kind of takeaway that I'll just say is that they use basically the same thermal barrier and air barrier that we saw used in Finch Cambridge and a lot of other projects. So even though this is a steel frame, you know, metal frame building, they're using some of the same materials. A big difference here, this project, Finch Cambridge, that mineral wool, I believe is 2 inches thick. On this project, they use 5 inches of mineral wool. And a big reason for that is simply because of the thermal bridging impact of the metal versus the thermal bridging impact of the wood in this case. This is one slide on thermal bridging. Again, this is something we can talk more about next week. This is just showing you what we kind of mean, heat transfers through materials with higher conductivity, wood, metal, concrete, etc. Passive house requires a focus on reducing the amount of thermal bridges and mitigating the impact of the ones that do exist. And this thermal image on the right is just showing you, we're on the inside of a house looking out, and you can see the wood studs very clearly. You can also see the fasteners very clearly. So whether those are screws or nails, either way, they're a piece of metal there that you can clearly see is transmitting heat directly through that wall. So we want to minimize that impact on our buildings. So that's building envelope systems. So now let's talk about the mechanical system. So the building envelope systems, we're reducing heat losses. Now the mechanical systems, let's make up for that with our heat gain. So we're not going to get into it this section, but we do have solar heat gain and we have internal heat gain from us, as we mentioned. But generally, that's not going to be enough. We do need some mechanical sources. Those are going to be divided generally into heating, cooling, ventilation, and hot water. I'm going to go, this is a very, very quick overview on mechanical systems. We'll go more into mechanical system sizing and design next week. This just gives you kind of a general introduction to the ventilation and to the heating and cooling systems. We're not really going to talk about water right now. So when it comes to ventilation, we are providing a balanced, continuously running ventilation system. you're pretty much always going to see something called an energy recovery ventilator or a heat recovery ventilator. So ERV or HRV, heat recovery ventilator or energy recovery ventilator. These are two terms that are used to describe something that is pretty much the same thing, with a very, very kind of minor difference between them. The minor difference kind of relates to how they tend to deal with humidity. Energy recovery ventilators deal a little bit better with humidity. So in this climate, we tend to see energy recovery ventilators used more often, ERVs. But either way, these systems work the same way. They're going to be continuously running, so they're not cycling on and off. They're always running. They may have different speeds, different fan speeds that can increase or decrease, but always going to be on. You can think of these as the lungs of the building. You probably heard the old adage, homes need to breathe. I hear that a lot when I talk about air tightness of a building. People are always raising their hand and saying yes, but doesn't a home need to breathe? Yes, but not through holes in the body. It needs to breathe through a dedicated respiratory system, and that's what we provide with this. These are the lungs, and they're always working. In addition to kind of constantly providing air, is also filtering that air constantly. So if we're talking about a winter time period, you're taking that warm air that's inside, that's dirty, and you're taking it out, and then you're taking air from the outside and you're bringing it in. And that air you're bringing in, you are filtering. So you're getting a high level of clean air coming in to the space. We're also recovering heat energy from that outgoing air. That's why these are called energy recovery ventilators. Typically, we're recovering 80% or more of that outgoing heat energy. So what that means is that air on the inside, say today it's 68 degrees inside, perhaps that's what you have it heated to, that air that you're taking outside, when it passes through this ventilator, it's going through a core in the middle, a heat recovery core, that's able to take some of that heat energy out of it. And then when that incoming air, that cold incoming air from the outside comes in, that heat energy transfers to that incoming air, effectively preheating it. And it does that without mixing the air that you might see in a traditional ventilation system. Incredible concept that we do with these ventilation systems. So it doesn't mix the ingoing and outgoing air, recover some of the heat energy, and also provides ventilation at the same time. So that's ventilation. When it comes to heating and cooling, there's different options. But when we kind of zero in on it and kind of look at the common features of all these different projects I've been showing you, it's pretty much always going to be some type of air source heat pump or a VRF system that works very similar to an air source heat pump. I do see, for those kind of curious, I do see geothermal used sometimes, and there's other heating systems out there that we do see sometimes. So these are not, like to say, the only things, but this is the vast majority of projects are using air source heat pumps or similar VRF system. These systems, for those unfamiliar, are all electric. So they're running on electricity, and they're providing both heating and cooling. So depending on what you need at the time, they're providing heating or cooling. And they're incredibly efficient, about 200 to 400% efficiency. So if you think, your electric, if you have familiar with electric baseboard, you probably heard, uses a lot of electricity, it's expensive. That's because it's only 100% efficient. These ones are at least twice as efficient, if not 3 to 4 times as efficient. A new gas furnace might be that 96% efficiency, 98% efficiency. What that basically means is the amount of energy you're putting into the system to run it, you're getting 2 to 4 times as much heat energy out of it. And you're doing that because you're not converting electricity into heat. You're using electricity to power the compressor that's in this system. And that compressor is compressing air and extracting heat energy out of it. And that's heat energy is what's producing heat. And you're able to extract a greater amount of heat energy from compressing the air than the comparable amount of energy you're putting into the system. These can be ducted systems or ductless systems. So both things are allowed, are out there. And if you're doing some type of renovation on a house that, say, already has a forced hot air system, you can usually kind of configure this to maybe use a similar type of ventilation system, so you don't have to kind of redo everything. There's also a lot of cold climate models. I get a lot of questions sometimes talking about this for folks who have kind of heard about these, maybe 5 5 years ago, and they were like, oh, these don't work in our climate. They do now. There's tons of cold climate models that work very efficiently in colder climates. So that's less of a concern. So I got 2 slides left, and then I'll go to questions from you guys. So the final 2 slides are just going to share some lessons learned from some of these first projects in this area. This slide is going to go over the design phase. The next slide will go over the construction phase and just share lessons learned. Number 1, bring together your team early. So as quickly as possible, get your passive house, consultant or designer on board, but also bring your verifier or passive house certifier on as early as you can. Get them early on, giving you feedback on your project. Make sure your mechanical engineer is involved in that project early so that you can design the mechanical system in the right way. Pay attention to your critical barriers. I talked a lot about thermal and air today, and I'm going to continue to talk about those in every one of these sessions, but also keep in mind water and vapor. Those are also important. Just make sure you know where those barriers are. The best advice everyone gives is to every drawing that is being submitted or being sent to, say, the GC, have it in color and have your air barrier highlighted, have your thermal barrier highlighted in a different color. Make sure it's easily communicated and easily noticeable about where your air barrier is, what materials are making up that air barrier, what materials are making up the transition from one barrier to the next, and so on. Work with mechanical engineer experience in low energy buildings. I'll admit, not every mechanical engineer you talk to is going to have experience with passive house. That's the reality right now. And years down the road, they'll probably all have experience with passive house. But at this point, you're not going to find that everyone does. What you want to do, though, and that's okay. What you want to do is find somebody who's just experienced with the concept of lower energy buildings or understands, not how to oversize a system. That's a big pitfall in passive house, would be oversizing the mechanical system. So you just want to make sure that you're working with somebody who understands, concepts of not oversizing the systems and how to properly size them for a low energy building. And consult with your contractors and your trades as early as possible. Bring them on in the design process. Really focus on the constructability of your design, the constructability of the materials you're using. Keep in mind your air barrier is only as effective as how it's built in the field. So always keep that in mind, and so bringing folks into the process early to weigh in, especially on how comfortable are those trades going to be able to put this up? Do they need extra training? Maybe there's a different material that you can use that they're more familiar with, that they're going to be more effective at implementing. Think about those things. Compartmentalization, solar heat gain. I'm going to talk too much about those. I kind of hit on a little bit of them. Construction phase. So once you get to the construction phase, hold kickoff meetings. This is very important. These can take all kinds of different forms, but the point of these are simply having dedicated forums for communication to stress, what are the passive house details. We all know there's going to be different people on that site every day. There's going to be trades there one week that are not there the next, and trades not there one week when you run a meeting who are going to be there the next week. So make sure you're finding regular ways to have meetings, bring people up to speed on what they need to know about the passive house details. Use mock-ups on site. These have been incredibly important. Sometimes they're, they look like this that you see in the image. Sometimes they're just kind of a small wall, but use mock-ups to kind of show how is this air barrier being installed? What's the best way to apply the tape? Like manufacturer reps, whether it's, the air barrier manufacturer, the thermal insulation manufacturer, maybe the person who's making the particular, clips that you're using to attach something. These reps will come out, help you figure out how to install them, and even spend time with your teams teaching them. Know your air barrier. Again, common theme coming up on every slide. But know where your air barrier is. Make sure that all the trades know where it is. A good tip that people have raised is to just assign somebody on site to sort of be your air barrier manager. This could be somebody from the GC. Usually, it could be somebody from another part of the team, but usually from there, who's just in charge of monitoring that, making sure everybody's up to speed, doing some kind of walkthroughs every now and then, and conduct blower door tests early and often. You need to do one to confirm the air tightness at the end. That's your final certification, but do them earlier. The recommendation at this point is to do them 3 times. I have seen multiple teams do these 5 times, but 3 times is generally the recommended time. So do them once you have sort of once you have your full envelope up, so once windows and doors are installed, your air barrier is installed on the outside, run a blower door test. The reason you want to do something early is it's going to be easier and cheaper to fix any issues that you have the earlier you identify them. That's kind of the biggest reason to do this. So those are the big takeaways. Those are sort of the lessons from early teams. So we went over a lot today. This was an introduction. We covered a lot of things from metrics to lessons learned to some examples of projects, lots of different things. But I'm going to pause now. Thank all of you guys for being here and sitting through this. And I'm going to take questions. So if you have any, please let me know.
Thanks, Aaron. Yes, there are some questions that came in.
Okay.
Okay, first one is, and you might have touched on this since these ones came from a little earlier in the beginning. Are there examples of insulated concrete form, like ICF passive house construction?
Yeah, there are. So I would say it's not common. It's not something I see a lot, but there are definitely ICF being used. I've seen some projects in New York that have used it, and I believe there's a project in Newburyport here in Massachusetts that used ICF. So it's not common, but it's definitely something to see.
Okay.
But in terms of sharing the most common things that I see, it's not there.
Great, thanks. Okay, next, you mentioned a statistic that by 2018, passive house projects were about 2% less on average construction costs compared to other projects. So the question in regards to that is, are there any case studies of working with municipal planning and zoning commissions to encourage the incorporation of passive house standards into builds and retrofits?
Excellent question. So first, just to clarify that statistic, where that came from, just so we all know, that came from the Pennsylvania Housing Financing Association, and that was looking at the buildings that received affordable housing financing through them, and it was comparing the ones that were passive house that achieved financing to the ones that were not passive house that achieved financing. And in that year, in 2018, the bucket of ones that were passive house were on average 2% less. So that's just to clarify what we're talking about with those numbers. And then as far as case studies on this, yes. So I can't speak to as much as happening in Connecticut, and my apologies for that. So my examples are going to be here from Massachusetts, but I have two good ones that you can look at. The first is the town of Newton. They did a really excellent program. It was actually led by a community group called Green Newton, who was really took a lead on advocating for their city council to incorporate very strict building policies in their climate action plan. And they eventually got passive house in that. So not in the sense that passive house was required, but through some zoning initiatives, they were able to highly suggest it. And in that project that I showed you a while ago, that one that was Northland, that I said about 8 buildings were being constructed a passive house, that developer was originally pushed to do passive house in the first place because of this initiative. They were going through the zoning process, and they were being highly encouraged by this climate action plan that had building efficiency in it to explore passive house. So what they went through there is a really kind of good example of how to do that. The other town in the area is Somerville. Somerville incorporated a zoning initiative that did require passive house in certain high density districts, so high development districts, and they did it through a way that awarded density bonuses for projects that were pursuing passive house. So maybe requirement isn't the right word, but through the way they wrote it, it was effectively a requirement for any real building that wanted to pursue development in that area. So we are seeing kind of ways in which towns and cities are exploring zoning initiatives to encourage passive house.
Great, thank you. Another one. So with assuming or just knowing that the construction quality is higher using passive house standards, can we expect, though, that the tapes, adhesives, and air barriers will last for the long run?
Yeah, yes, definitely. The ones that are, I mean, if you're doing it as recommended as it's supposed to be installed. Yes, these things have. Now, obviously, we don't have a passive house that was built 60 years ago using this to look at. So a lot of what we're talking about is modeled study data, but there has been studies on the how long these things can last, on what happens to something where even UV light is exposed to it for an extended period of time. These other sort of things. So I think there's plenty out there, both from manufacturers and from more independent non-manufacturer sources to show that these things will. Yeah. Again, the biggest issue that comes up is not around like the product failing because of some inherent aspect of the product, but because something happened during the application that wasn't supposed to. Wasn't installed correctly. The tape wasn't adhered flat. It had bubbles in it or something. These type of things can cause issues, but when things are applied correctly, we're not seeing those.
Okay. How do exterior walls pass air sealing tests on retrofit buildings? Especially when exterior looks original on many, especially brick-faced ones.
Yeah, exactly like that. The Tyler one, which is that retrofit of an old school, which is all brick. So first is through they're doing, when you see a building like that keeps the old facade, we see that especially in a lot of cases to say a historic renovation where keeping that old facade is critically important. Everything's being done on the inside. Now, how are you doing that? It is a challenge. And on retrofits, that is an enormous challenge that you don't face on new builds, because you have to come up with a way to do that with the retrofit itself and maintaining that. So there's a lot of different strategies that are implemented, but you have to do it on the inside. And it's going to be around using different air barrier systems and then paying critical attention to how you're connecting them. So that inside wall might have one air barrier system, and then when you get to the next floor, you have another air barrier system. How are you connecting those? Are they connecting to the floor? And if so, is the floor sealed? I mean, you have to it's just about paying critical attention to all those things. One product that I see used in retrofits that I don't see in new buildings as often is something called aero barrier, I want to call it, air barrier seal. It's actually a vaporized sealant. So you'll actually pressurize the building, say with a blower door, you'll pressurize the building and run this vapor sealant on the inside of the building, and it'll go and kind of seal different cracks and things in the envelope. So that's also kind of a method is using some product like that.
Okay. Going to the barriers, the 4 barriers you mentioned, someone is asking, they might have missed one of them. So the first one was air, second one is heat, third is water, and what's the fourth?
Vapor.
Vapor.
So you have air, you then have heat or thermal, heat or thermal, kind of same, just different terminology, and then your water barrier and your vapor barrier. So water and vapor are kind of, they are very similar, but generally water, we're talking about bulk water, and vapor, we're talking about water vapor. So they're similar, but they interact with materials in a different way, which is why we consider them as different barriers.
Okay, and then another question in regards to the vapor barrier. Is a vapor barrier required in passive house construction which has a tight air barrier?
Yeah, so no, it's not. In fact, a lot of these projects I've showed you are vapor open. In fact, the one we're looking at right here, Finch Cambridge on the top of this slide, is a vapor open assembly. By that, I mean it has no dedicated vapor barrier. It has an air barrier membrane. The air barrier membrane in this case is a Siga, very thin membrane, and that membrane stops air transfer, but it is vapor permeable. So water vapor can move through it. What this means is that the assembly can dry out to the outside, and then there is what's called that rain screen. So the vapor can move through the air barrier. On top of the air barrier is mineral wool insulation, which resists bulk water. So it's a water barrier, but it allows the transfer of water vapor. So it's vapor permeable. So the vapor can go through there. And then you have the siding, where you have a gap, and that gap allows the vapor to go up and out, because there's also a gap up at the top. So the vapor goes out. So that's how vapor is being controlled in that system. So even though there's not what I would call a vapor barrier, there is a vapor control method.
Okay. And let's see, another one came in. This might be the last question. What do you do if the final blower door test results are not satisfactory?
Yeah. You figure out what you can do to improve it and then run another one. Quite frankly, I mean, the blower door test, that is why I kind of emphasize it so often and kind of bring out that one slide where I was like, this is the number teams are focused on, is because you have to hit it. Passive house is, I mean, that might be a drawback depending on where you're coming from, but the reality is that passive house is metric driven and you have to hit those metrics. So you have to hit the blower door test. This is why we recommend teams do run them early and often so that you can identify if you're behind on where you need to be. But if you run the final one, hopefully you're not too far behind. Hopefully there's things you can find. And there's lots of different methods for doing this. Probably some of the most successful things I've seen teams do is when they run a blower door is to at the same time use a smoke machine on the inside. And you can see where that smoke goes. If you have the pressure, so the inside of the house is pressurized, you can stand on the outside and see the smoke coming out. And that can quickly identify leaks that you might not have noticed before. And all it might take is a little, fixing of the air sealing on those particular spots. Might be what you need to do. Sometimes there's not major things that are causing the reason that you're failing. There's kind of little things in different spaces, or one thing in one space. So smoke can do it. There's other kind of methods like that that can help you kind of identify where the air is going. That aero barrier kind of thing that I mentioned that I see in retrofits, that's also something that you could use in an emergency situation and just run it inside of a building, and hopefully that will kind of address an issue. But bottom line, you have to find what you can fix and do it. So run them earlier. Run them as often as you can to identify those leaks early.
Another question came in. How often have you seen blower tests fail? Is it common?
So now that it's sort of become regular practice to run them more often, to do earlier tests, this failing them is not common. That came about because people did fail them, but now that we're doing them more often, we're sort of identifying any issues that come up in a very early stage where it's very easy to address it. We're not seeing projects fail at that endpoint. And I think that's just kind of some of the big takeaways. Make sure you're paying attention to that air barrier, and running the blower door test at an earlier stage really, really helps you figure out if you're there or not. Yeah, so I think that's the biggest thing. Hope that answered the question. I know it's a worry. It is. I mean, you have to hit that metric. It's a worry when you're going down and you put all this into it and you get to that point, like, oh no, we didn't hit it. But run them early, see where you're at, pay attention to it. And if you're doing everything right, I mean, if you're paying attention to all these areas, you're getting the details right, your team knows what they're doing, you're probably going to be just fine. And most of these projects I showed you, all these, in fact, nearly all of these, I'd probably say the Tyler, the retrofit might be exempt from what I'm about to say, but most of these projects have blown that away. 0.6 is what they needed to hit. They're 0.5 and lower. I mean, they're doing just fine.
Right. Okay, I think one more question or two that came in. Are blower door machines expensive?
Yeah, I guess that's a relative term. I don't know. So what we see, I guess, I don't know the cost. I think the better way to phrase it is kind of where is that coming from? So in some cases, your passive verifier will be maybe supplying that. That's one of their equipment. When you bring them on, that's just something they have. So that's not necessarily like as a GC, something you're going to say, oh, we need to buy a blower door test. It might be that the passive verifier, this is part of what they supply in their package of being a verifier. You might hire just a separate blower door consultant, like an air barrier consultant who runs it, who brings one in. The different projects approach it in different ways. So I don't have a good answer for how much it would cost for a project that normally doesn't run one to bring one on and run it, but usually it's going to be part of the verification process.
Okay. And yeah, that was another question. Basically, would you recommend that the builder buy and provide the blower door?
Yeah. I mean, so I just said, the verifier might have them, bring them on. But honestly, the answer is yes. If you as a GC or a builder have the, capability to do that, do it. Because I think for a couple of reasons. One, being able to have the flexibility to run them often is going to just be to your benefit. And I think that will make up for any costs in the long run. And second, it gives you the flexibility to use these on your non-pass house jobs where you may not be hiring a pass house verifier to come in. Because I think it's valuable on any project. And I don't, know exactly what's happening with the building code in Connecticut. I know in Massachusetts where you're going to run a blower door test on any project, but whether you're hitting pass house or not, the metric you're trying to achieve is going to vary, but you're going to run a blower door test no matter what. So I would say yes. I think more folks should be using them on every project. And even if you're not trying to hit that 0.6 passive house metric on your non-pass house project, maybe you have a different goal. Maybe you're trying to hit 1 or something else. But it's always good to pay attention to the airtime.
Okay. It is 1:31, so we do have to wrap it up. If there are any additional questions we haven't got to, you can email the Passive House Training CT at icf.com, and I can hopefully answer them or relay them to Aaron. But yeah, thanks, Aaron, for this great 101. I put in the chat the registration link to next week's 201, which will be at the same time next Thursday. So hopefully everyone can join us then to dive a little deeper into the topics Aaron mentioned. And yeah, thanks again to the sponsors of Energize Connecticut to bring this training to all of you today. I hope everyone enjoyed. Thanks, Aaron.
Mm-hmm. Thank you.
Yeah, okay. Have a good rest of the day, everyone. Thank you. Bye.